Hello, class 10. The topic that we are going to start today is electric current. Now, this is a topic that we've dealt with in class 9 also. Okay, we discussed about electric current, we discussed about, charges, free charges, okay, and we discussed about potential, we also discussed about resistance, factors affecting resistance of a conductor, and we'd also discussed about Ohm's law in class 9. If you turn the pages of your exercise book from class 9, you will see all of these topics, dealt with in class 9 itself. Now, the very first thing that we are going to discuss here in class 10 under this heading of cars is, all of these topics that we've already done in class 9. Although Ohm's law was not there in your class 9 syllabus, I had already dealt with class 9. I had already dealt with Ohm's law in class 9 itself, so that it becomes easier for you in class 10. Okay, so it's kind of only a revision for you all. We are going to discuss the same things that we've discussed in class 9 itself. Okay, so let's start with the recap. Let's start therefore with the definition of electric current. Electric current is the rate of flow of charge. That is how we define electric current. Now, when we say flow of charge, when we refer to charges, what we are referring to is free charges, or so to say, to be more precise, free electrons. Any conductor will have, its electrons going round about the nucleus, any substance for that matter. Okay, so in case of conductors, what happens is the valence electron can easily come out of the valence orbit and roam about freely inside the substance. Okay, so that freely roaming electron, it can freely move about inside the substance itself. Okay, that is what is called a free electron. And whenever we say flow of charges, we are referring to the flow of these free electrons only. We are strictly speaking only about the free electrons. Get that in very, very clearly. Okay, we are not talking about the electrons going around about the nucleus in whatever orbit. Okay, we are only talking about the flow of free electrons. So, if Q charges or Q amount of charges are flowing in time t, then the current I, be it capital I, small I, okay, the current I is defined by rate of flow of charge, or so to say, Q divided by T. How many charges are flowing in a certain time? That is what is called electric current. The more charges flowing in a certain time, the more the current flowing, of course. The lesser the charges flowing, the lesser the current. Okay, the lesser the charges flowing in a certain time, the lesser the current. Do you remember that? Now, unit of charge, first of all, unit of charges, Coulomb, C-O-U-L-O-M-B, from the name of a person, of course. Okay, you've discussed this in class 9 itself, is denoted by a capital C. Coulomb, the unit of time is second, therefore, unit of electric current, when I write current, I mean electric current, okay. So, unit of electric current is ampere, denoted by a capital A. And ampere is coulomb per second. This is coulomb per second, remember. Coulomb per second is what is called ampere. So this is about electric current, remember. Oh, by the way, one more thing let me tell you. If, say for example, you have a power source, this symbol represents a cell, a power source. If you have a combination of cells, that is what is called a battery, remember. So this symbol is representing a resistor. Okay, resistor is basically any conductor. Conductors having high value of resistance is what is called a resistor. So to say, bad conductors are what are called resistors, remember. So this is a bad conductor, so to say. So you have a conductor, or a bad conductor rather, having resistance R and current. Remember, by convention, current flows from the positive terminal of the battery. The longer vertical line represents the positive terminal and the shorter line represents the negative terminal. Do remember, by convention, current always flows from the positive terminal of the battery to its negative terminal outside the battery, whereas inside the battery it flows from the negative terminal to the positive terminal. And mind you, current always flows only when there is a closed circuit, closed loop. If somehow the circuit breaks over here, okay, then the current of course is not going to flow, mind you. Now, though we've said that current is the rate of flow of charges, or so to say, current is the rate of flow of free electrons, to be more precise, and electrons being negatively charged, electrons always electrons, they are attracted towards the positive terminal. So to say, electrons, free electrons are actually moving in this direction towards the positive terminal because they are, attracted by the positive terminal. Okay, so, and we see that current is flowing in the opposite direction to the flow of flow of free electrons. So, do remember, although current actually arises because of the flow of free electrons, we, by convention, by agreement, the flow of current is opposite to the direction of flow of free electrons. Remember that. I had told you the reason in class 9 itself. Okay, class 9 also I told you why this happens actually. Okay, because when the direction of current was agreed upon, top scientists from all over the world, they got together and they decided, okay, we will, decide that current flows from the positive terminal of the battery to the negative terminal. Okay, and once they decided, once they had agreed on this, then after some years, electron got discovered, and they got to know that current arises because of the flow of electrons. Okay, and they also got to know that electrons flow in the opposite direction, but they've stuck to the same convention, same agreement. Till date we have stuck to the same agreement, remember. Okay, so do remember, current flows from the positive terminal to the negative terminal, always remember that. Though none of us have so till date seen current flowing, okay, I take a while, I don't see current flowing, but this direction of current is by convention or by agreement, like I've already mentioned. So this is about electric current. Let's talk about, you can copy this if you wish to. You can pause the video and copy this. Let's talk about electric potential. Electric potential, or rather, let's talk about potential difference. This is more important. Potential difference is more important for you. Potential difference. Now remember, whenever you hear the word potential, be it potential difference, electric potential, or potential energy, gravitational potential energy, static potential energy, okay, whenever you hear the word potential, you have to understand that it has got something to do with work done. Okay, what is gravitational potential energy? The work that I do to lift this piece of chalk or any body from a certain height to a point high above it. Okay, so to a higher point we lift a body, then to lift it up we have to do work, we meaning an external agent. Why? Because this body is all the time being pulled by the force of gravity. So the force of gravity is all the time pulling the body, but opposing the force of gravity or against the force of gravity, I am lifting this body up. So to lift this body up, obviously I have to do work. Okay, now whatever work I do to lift this body up, the same amount of work is stored in this body as potential energy. Alright, so potential energy basically means, or rather the word potential basically means work done. And what is potential difference? If I have 2 points, say point A and point B, then the potential difference between these 2 points A and B is, okay, let us also join these 2 points A and B by a wire or a line. So the work done to take a charge, or rather a unit charge, from point A to point B is what is called the potential difference between these 2 points. Okay, so the work done to take a unit charge from point A to point B is what is called the potential difference between these 2 points. And electric potential is also basically potential difference only. Alright, if this point, say point A is at infinity, and you want to find the potential at this point B, you want to find the electric potential, so to say, of this point B, then the work done to bring a unit charge, unit positive charge to be more precise, the charge has to be positive. So A is here infinity. The work done to bring a unit positive charge from infinity to this point is what is called the electric potential of this point B. Whichever point you are taking the unit positive charge to, say this is point C, point A again is infinity, the work done to bring a unit positive charge from infinity to point C, following whatever kind of a path, be it a straight path or whatever kind of a path, the path is not important. What is important is the work that you do to bring a unit positive charge from infinity to a certain point is called the electric potential of that point. Okay, and we consider the potential of infinity to be 0. Alright, so electric potential is basically potential difference between the potential of this point and the potential at infinity. So electric potential of this point minus the potential of infinity, which is 0, gives us the potential difference between these 2 points. Alright, so remember, electric potential basically is potential difference, and you have to pay more attention to this word, to these 2 words, okay? Potential difference. So what is potential difference? Potential difference, like I've said, is the work done to bring a unit positive charge from one point to the other. This point be infinity or whichever point under consideration. So let us suppose, okay, so let us only consider points A and B. Whatever be the distance between them, whatever be the separation between these 2 points, if W is the work done to take charge Q from A to B, say for example. Okay, so to take Q amount of charge from point A, from a certain point A to another point B, the work done is W. So to take Q amount of charge, work done is W. Alright, and therefore to take a unit positive charge, Q is positive, to take a unit positive charge, unit means 1, don't forget. So to take a unit positive charge, the work done will be W by Q. Now this is what is called the potential difference between these 2 points, and the potential difference is VA minus VB, where say VA is the potential at point A, electric potential at point A, and VB is the electric potential at point B. Alright, so the potential difference between these 2 points A and B is W by Q, is the work done to take a unit positive charge from one point to the other. Alright, so do remember that potential difference between, I will write here again, potential difference between these 2 points, VA minus VB, or potential difference between any 2 points for that matter, is given by the work done to take a unit positive charge from one point to the other. No one is going to ask you what is potential difference or define potential difference, but you need to understand, remember it. Okay, because time and again in this particular topic we are going to talk about potential difference, which basically is work done, remember. So let me erase this also. This is about electric potential or potential difference, so to say. Now we have resistance. What is resistance? Resistance is the opposition to the flow of current. Any conductor will have resistance, remember. A good conductor will have low resistance, low opposition to the flow of electric current. A bad conductor will have a high value of resistance, remember that. So resistance basically is, it is the opposition to the flow of electric current. So this is your resistance, and let us also talk about factors affecting resistance. If you check your class 10 exercise book, we've written all of these notes there. All of these notes you will find there in class 9 exercise book. So the first factor affecting resistance of a conductor is length of the conductor. Okay, let's say L is the length of the conductor. So if resistance is R, if resistance is denoted by a capital R, then resistance is directly proportional to the length of the conductor. So to say, longer the length of the conductor, more is the resistance of the conductor. Shorter the length of the conductor, lesser is the resistance of the conductor. No length, no resistance, of course. So to say, if I have two wires, two conductors, made up of the same material, exactly the same material, okay, they have the same thickness, alright, so to say they have the same cross-sectional area, but one is longer and the other is shorter one, alright, one is longer and the other is shorter one. So remember, although they are made up of the same material, they have the same cross-sectional area, but still the longer one will have a larger resistance and the shorter one will have lesser resistance. The longer one will have more resistance and the shorter one will have lesser resistance, remember that. And I have given you the example of two corridors of exactly the same width, alright, and one is longer but the other one is a shorter corridor, and you have at regular intervals we have certain number of people. Okay, and you want to cross that thing, you want to cross the corridor, go from one end to the other. Alright, so in which of the corridors will it will be difficult for you to cross? Okay, obviously in the longer corridor. You have a crowd of people in both of the corridors, so in which of the corridors you will find difficulty to go from one end to the other? Obviously the longer corridor. Same thing happens exactly in case of electric current also. The longer the length, the more resistance the electric current experiences. And shorter the length, shorter the resistance, of course. The second factor is cross-sectional area. Cross-sectional area, of course that of the wire, remember. If A is the cross-sectional area, then resistance is inversely proportional to the cross-sectional area. That is, more is the cross-sectional area, greater the thickness, so to say, lesser the resistance, lesser the thickness, lesser the cross-sectional area, more is the resistance. Again, you can take the example of the same two corridors, but in this case, one corridor is wider, the other one is a narrow corridor. So again you have people in the corridor. Okay, so you say the two corridors are of equal length and you have equal number of people in the two corridors, say for example. One of the corridors is a narrow one and the other is a wider one. You have equal number of people in the corridor standing, crowd of people, and the length of the corridor is the same. Now, in which of the corridors will it be easier for you to move from one end to the other? Obviously the wider one. So it's the same thing here. Okay, so this is dependence of resistance on the length of the conductor and cross-section area. We have two more factors. For that, let me erase the definition of resistance, which no one is going to ask you. So, the third one is temperature of the conductor. Temperature of the conductor. Okay, now how is it dependent? More the temperature, more is the resistance. More the temperature, more is the resistance. More is the resistance. Remember this. Now these are all points that we discussed. Okay. Now what happens is, as the temperature increases, now what causes the resistance? It is the number of ions and electrons also. Okay, number of ions, basically number of ions and atoms that you have inside a conductor, that causes resistance or opposition to the flow of electric current. Now as the temperature increases, what happens is the ions and the atoms, they start vibrating. So there's more chances of the free electrons that are nicely roaming about freely inside the substance. Okay, there is more chances of this free electron colliding with a moving, very fast moving ions and atoms. Alright, the faster the atoms and ions are moving, which is possible as you go on raising the temperature of the conductor. As you raise the temperature, what happens is the atoms and molecules, they start moving faster. So ions and atoms, they are moving faster, and faster or more vigorously they are moving. Okay, there is more chances of a collision with free electrons, and more the collision free electrons encounter on its way from one end of the conductor to the other end, what happens is the more so to say the resistance it experiences. Okay, so this is why higher the temperature of a conductor, more is the resistance. And finally, the fourth factor, let me erase the heading. The fourth factor is simply the nature of the conductor. This we've already discussed too. Nature of the conductor. Now, what does this point tell us? It tells us that good conductors have lesser resistance, bad conductors have more resistance. That's it. Okay? Good conductors, they have lesser resistance. I hope you've copied this length of the conductor. And bad conductors, they have more resistance. Okay, so these are the four factors on which resistance of a conductor depends. Let me again write this first point. R is proportional to the length of the conductor. If this is my relation number 1 and this is my relation number 2, let me write over here now in this right hand corner space, bottom corner. Now if I combine these 2 points or these 2 relations, I can write R is proportional to L upon A. Now this proportionality sign can always be replaced by an equal to sign, provided we add some constant. So R is equal to some constant rho, RH or rho. This is a Greek letter, of course, and rho is called specific resistance, or it is simply called resistivity. So this is what your rho is, remember. Rho is called a specific resistance or your resistivity, a very, very important equation for you all here. R is equal to rho L by A is a very, very important equation for you all. Rho, like I said, is a Greek letter. It is called specific resistance or resistivity. Should I? Okay, let me just check what is the